On October 3, 2025, as 3I Atlas swept past Mars on its inward approach to the Sun, two orbiting spacecraft captured a sequence of images that immediately caught astronomers off guard. The trajectory they calculated from those measurements didn't align with the earlier models we'd been using. Instead, the new data tightened 3I Atlas's path by nearly an order of magnitude, a level of precision we've never achieved for an interstellar object, this faint, this distant, and this fast-moving. And that precision created a new problem. When scientists compared the Mars-based measurements with its earlier color shifts, irregular brightening, and CO2-rich chemistry, several pieces no longer fit neatly together. The trajectory is clearer than ever, but the behavior driving it is still not fully explained. In this video, we'll walk through exactly what the Mars spacecraft saw, why the refined path challenges our expectations, and what it might reveal about an object that entered our solar system from another star. If you're finding value in this deep dive, gently tap that like button and subscribe. Tell me in the comments where you're listening from, what time it is there, and what you think is the most compelling anomaly about 3I Atlas. The first thing scientists noticed in the Mars imagery was how compact the coma looked. Not large, not billowing, not fragmented, but tight and asymmetric, almost as if activity was coming from a constrained region rather than the full surface. This is reported in the preliminary Mars orbiter photometry, though the full peer-reviewed analysis is still pending. What is confirmed is that this compact coma made trajectory calculations unusually clean. With fewer diffuse structures to confuse the centroid, the orbit could be constrained more precisely. The result? A trajectory solution nearly 10 times tighter than previous Earth-based models. But this clarity also exposed something odd. If the coma is unusually compact, why did earlier brightness spikes show such strong variability? And why did color measurements shift toward the blue in ways more consistent with carbon-rich outgassing than with dust-driven brightening? Those spectral signatures come from reported telescope data, but have not yet been fully reconciled with the new Mars observations. The missing dust is another problem. In many images from Earth and from space observatories, the dust tail is either extremely faint or effectively absent. A gas-dominated coma isn't unheard of, especially for small or CO2-rich comets. But for an interstellar object approaching the Sun, it's unexpected. Preliminary explanations suggest that the nucleus may be unusually poor in dust-forming silicates, or that the dust grains are too large to scatter light efficiently. These ideas are proposed in ongoing research, but are not yet confirmed. Then there's the timing. The Mars orbiter observations were captured just as 3I Atlas was undergoing subtle photometric changes, slight increases in brightness followed by abrupt plateaus. Not explosive outbursts like those seen in perihelion comets, but irregular boosts that don't follow the smooth thermal curve predicted by standard sublimation models. One working hypothesis is that the surface layers are patchy, with pockets of CO2 ice exposed at different times. When these patches activate, they can cause short-lived increases in gas flow, tightening or loosening the coma. This explanation is consistent with several published models of CO2-driven comets, but researchers have noted that 3I Atlas's CO2 levels appear unusually high even by those standards. Another line of investigation focuses on the radiation-processed crust, the hardened outer shell that interstellar objects accumulate after billions of years in deep space. If the crust is especially thick or uneven, it might release gases only through cracks or vents, producing the asymmetric activity we see. JWST results have hinted at this possibility, though the depth and structure of the crust are still models, not confirmed measurements. But the most intriguing part of the Mars data isn't the coma or the chemistry. It's the way the refined trajectory aligns, or rather, doesn't perfectly align with the expected non-gravitational forces from outgassing. The trajectory is clean, but the activity pattern is messy. And when those two don't line up, scientists are forced to consider additional factors. Some of those factors are ordinary: rotational wobble, uneven sublimation, or delayed thermal response. All are plausible and part of known comet physics. Others are more speculative, such as internal layering or material transitions that could redirect jets unpredictably. These ideas are being discussed, but none are confirmed, and this mismatch, a precise trajectory paired with irregular outgassing signatures, is what set off the next wave of investigation. Because once researchers noticed the inconsistency, they turned to a different question. If 3I Atlas isn't following the usual energy balance patterns of a sun-heating comet, what exactly is shaping its path? That brings us to the deeper look at its motion, its speed, and the surprising implications of a trajectory far smoother than its physical behavior suggests. When astronomers overlaid the newly refined path onto the earlier motion data, they noticed something that had been easy to overlook before. 3I Atlas is moving along an unusually stable, nearly planar trajectory, with far fewer perturbations than expected for a comet showing inconsistent outgassing. In natural comets, especially near the inner solar system, jets of sublimating gas act like tiny thrusters. They nudge the nucleus, causing measurable deviations. These non-gravitational accelerations are well documented across decades of comet research. Even modest activity leaves a fingerprint, a wobble, a drift, a curvature that can be traced back to specific jets. But so far, with 3I Atlas, that fingerprint seems faint, much fainter than models predicted based on its measured activity level. This doesn't mean the data is wrong, it simply means the physics is more complex than the simple models initially applied. Several teams have noted this discrepancy, though none have proposed a consensus explanation yet. One confirmed factor is speed. 3I Atlas is traveling at over 130,000 miles per hour, fast enough that modest jets exert comparatively smaller influence on its path. At this velocity, small non-gravitational forces dissolve into the noise. That part is straightforward and consistent with known physics. But even with that accounted for, the trajectory remains cleaner than expected. Some researchers propose that outgassing may be aligned more symmetrically than assumed, meaning any thrust-like effects cancel out. This is plausible, but not confirmed. Others have speculated that outgassing vents might be positioned in a way that aligns with the object's rotation axis, producing minimal sideways force. Again, possible but unverified. A more data-driven explanation involves the radiation-processed crust. If the outer shell is thick and rigid, it may be insulating the interior in a way that dampens rapid thermal changes. That would lead to smoother outgassing over time, even if the coma appears asymmetric to our eyes. JWST's early spectral hints support the idea of a hardened crust tens of feet deep, but the internal structure remains theoretical. What is clear and confirmed is this. Despite its irregular brightening and anomalous chemistry, 3I Atlas's motion through space behaves almost like a passive object, influenced primarily by gravity and only subtly by its own activity. And this brings up another interesting point. When astronomers ran the trajectory backward to determine where 3I Atlas came from, they found the path intersects the outer galactic regions with no clear parent star. This isn't unusual for interstellar objects. The chaotic gravitational landscape across billions of years makes precise origin tracing impossible. But what is unusual is how flat the path appears within our solar system. Most long-period comets approach at steep or irregular angles, influenced by the inclinations of the planets they've encountered. Interstellar objects tend to show similar randomness, but 3I Atlas's inclination is relatively low, giving it a smooth, almost planar motion, reminiscent of something that has been unbothered by the usual gravitational jostling. Is this meaningful? Possibly, but at this stage, it's still just an observation, not a conclusion. It does, however, raise a question that several papers have quietly hinted at. If 3I Atlas has truly wandered for billions of years, passing near stars and through turbulent galactic environments, how did it maintain such a stable, undisturbed trajectory? There are natural explanations, but they require specific conditions, and those conditions will guide the next step in analyzing its past and future motion. Because once the Mars data clarified its present path, astronomers turned their attention to something even more important. Where is 3I Atlas going next, and what does that reveal about its internal behavior as it leaves the Sun behind? once 3I Atlas passed perihelion and began drifting outward again. Astronomers faced the part of the story that matters most: how the comet behaves as it cools. This period, the weeks after closest approach, is where models are tested, revised, and sometimes overturned. And for interstellar objects, these post-encounter behaviors often reveal more than the approach ever does. For typical comets, the physics is predictable. As distance from the sun increases, sublimation slows, the coma shrinks, and the object's brightness fades along a well-understood thermal curve. Any deviation from this curve usually indicates structural changes, fragmentation, volatile layering, or exhaustion of surface ices. With 3I Atlas, early outbound measurements showed brightness fluctuations that didn't immediately settle. These weren't explosive outbursts like perihelion comets sometimes show, but subtle oscillations. Some telescopes reported minor increases, followed by abrupt plateaus, while others noted changes in the spectral shape of the coma. These results are reported through telescope logs and circulars, but still need full peer-reviewed analysis. One hypothesis is that the radiation-processed crust is beginning to fracture under thermal stress. If so, it could expose fresh material beneath the hardened shell, briefly increasing gas output before cooling again. This model is consistent with earlier observations of irradiated comets. But for 3I Atlas, the crust depth estimates ranging from dozens of feet to potentially more are still theoretical. Another possibility is tied to the unusual CO2 dominance in its chemistry. CO2 sublimates differently from water ice, often activating at lower temperatures and continuing to release gas even as the comet moves away from the sunday. If the interior is rich in CO2 pockets, these could fuel sporadic gas flows long after perihelion. This scenario is plausible, but not yet confirmed. But the outbound trajectory may hold the biggest clues. Now that Mars-based observations have locked in the comet's position with far more accuracy, astronomers can compare actual path changes with model-predicted non-gravitational forces. If 3I Atlas behaves like a standard comet, the outbound arc should begin to diverge subtly based on outgassing intensity. The angle, magnitude, and direction of that divergence can reveal how the nucleus is venting material. If, however, the outbound trajectory remains exceptionally clean, with deviations below expected thresholds, it suggests something else. Either the activity is weaker than the coma appearance implies, or the outgassing is aligned so symmetrically that lateral forces effectively cancel out. Both explanations are possible, but neither is typical. This discrepancy matters because trajectory deviations during the outbound phase often reveal internal structure, rotational state, and volatile distribution. For interstellar objects, these insights can point to how they were formed and how they've evolved over cosmic time. And here is where the Mars observations become crucial again. Because while telescopes on Earth are beginning to regain visibility of 3I Atlas, the spacecraft near Mars captured it from a completely different angle, giving astronomers a rare three-dimensional look at its coma flow and early outbound motion. Those preliminary reconstructions suggest a coma shape that remains asymmetric, even as the brightness stabilizes. It's a hint not yet confirmed that 3I Atlas may be venting from a limited region or fractured patch, rather than uniformly across its surface. If that's true, it would mean the comet's smooth trajectory is even more puzzling, because in most cases, asymmetric activity should produce measurable sideways acceleration. So, the next question becomes unavoidable. If the outgassing pattern appears uneven, yet the outbound trajectory remains unusually stable, what is moderating the forces acting on 3I Atlas as it leaves the inner solar system? To understand the mismatch between the activity pattern and the motion, astronomers revisited the physics governing outgassing. When a comet vents material, it produces directional thrust. However small, that thrust adds up. Over days or weeks, it should imprint a detectable curve or drift in the trajectory. With 3I Atlas, the early post-perihelion data shows far less deviation than expected for the level of gas release inferred from its coma and color measurements. One explanation is that the gas leaving the nucleus is expanding more slowly than assumed, which would reduce its ability to change the comet's motion. This could happen if the radiation crust is exceptionally dense, allowing only narrow, low-pressure vents. Some models of interstellar objects propose this kind of regulating shell, but it remains theoretical. Another possibility involves the nucleus's rotation state. If 3I, Atlas, rotates in a way that distributes gas release symmetrically over each full rotation, then short-term asymmetry would average out. This is consistent with how some solar system comets behave, but only if their rotation periods are known. For 3I, Atlas, no confirmed rotation period has been published yet. Reports exist of periodic brightness fluctuations that might correlate with spin, but these are still under review. Then there is the question of surface temperature gradients. If the crust is thick and thermally insulating, heat may not penetrate evenly, delaying internal sublimation and smoothing the gas flow over long periods. This would dampen sharp bursts and create a more predictable thrust profile. JWST's initial spectral results suggest a hardened surface layer altered by cosmic rays, supporting the idea of slow but steady interior heating. But a more intriguing hypothesis has emerged in some research discussions: internal layering. If the nucleus is stratified, alternating between radiation-processed layers and preserved primitive ices, the pattern of gas release could be governed by buried pockets reaching threshold temperatures at different depths. As each layer activates, the gas release might increase or decrease in controlled steps rather than chaotic bursts. This would produce a coma that looks irregular, but a trajectory that remains mostly smooth. This idea is speculative, but grounded in simulations of long-duration cosmic ray exposure. Still, even with these models, something feels incomplete, because the more precise the trajectory becomes, the clearer it is that the comet's motion is dominated overwhelmingly by gravity and only marginally by its own activity. That is normal for many interstellar visitors due to their high speeds. But the degree of consistency here, especially when mapped alongside irregular coma features, continues to prompt deeper investigation. This brings astronomers back to a fundamental question. Is the apparent mismatch a sign of unusual physics, or simply the result of observing an object that has spent billions of years evolving in environments very different from our own? To explore that, some teams are now comparing 3I, Atlas, not to typical comets, but to radiation-hardened bodies, objects whose surfaces have been modified by cosmic rays and high-energy particles. These bodies sometimes exhibit behaviors that blur the line between dusty comets and icy asteroids. If 3I, Atlas, shares characteristics with these transitional objects, it could explain why its activity looks irregular while its motion remains coherent. But this comparison leads to yet another question about its long-term evolution, one that astronomers are especially interested in. If the surface has been altered this extensively, what does that imply about the internal material that lies beneath the crust? And that question opens the door to a deeper investigation, one focused on the origins and ancient history of this interstellar traveler. To understand 3I, Atlas's core, astronomers first needed to understand its exterior, because the outer layers hold the imprint of its journey through interstellar space. According to models built from JWST's infrared spectra, the surface of 3I, Atlas, may have been transformed by billions of years of cosmic ray bombardment. High-energy particles can break molecular bonds, restructure ice crystals, and turn simple ices into complex, carbon-rich compounds. Over immense timescales, these processes can produce a crust tens of feet thick, a hardened, irregular shell that no longer reflects the comet's original composition. This process is well supported by laboratory simulations and radiation-irradiation studies of cometary materials. But what lies beneath that altered layer remains uncertain. One possibility, the conservative one, is that the interior still contains primitive ices from the comet's birth environment. If the crust is thick enough to shield deeper layers from radiation, then preserved material may exist below the hardened surface. This is scientifically significant because those deeper ices could reveal the chemistry of the stellar nursery, where 3I, Atlas, originally formed. However, this scenario remains speculative, until future observations can confirm changes in its post-perihelion spectrum. Another possibility involves thermal fracturing caused by its close approach to the Sunday. If the perihelion heating penetrated deeper than expected, sections of the crust may have cracked or peeled back, exposing fresh material. This could trigger delayed outgassing events as the newly exposed ices evaporate. Preliminary reports of minor post-perihelion brightening spikes align with this idea, though it is not yet peer-reviewed or confirmed. There is also a more complex idea that the interior of 3I, Atlas, may be heterogeneous, containing layers with different volatile concentrations and structural properties. This kind of internal composition has been observed in several solar system comets, where alternating bands of dust, water, ice, CO2 ice, and rock-like material form during their early assembly. If 3I, Atlas formed in a more volatile rich region around another star, its internal structure might be even more diverse. If so, the comet's present behavior, asymmetric jets, intermittent color shifts, irregular brightness changes, could reflect this internal diversity. Each layer reaching its sublimation point would activate briefly before settling down again, producing the subtle but real fluctuations we observe. But the most thought-provoking idea relates to the depth of radiation processing. If cosmic rays have penetrated farther than current models predict, the crust might extend deep enough that very little pristine material remains. In this case, 3I, Atlas, would be less a sample of another star system and more a record of the interstellar medium itself, shaped not by its birth environment, but by the billions of years it spent drifting between stars. This idea has begun appearing in scientific discussions, though cautiously. It reframes 3I, Atlas, not as a preserved relic of another solar system, but as a dynamic body that has spent most of its existence under the influence of cosmic forces rather than stellar ones. In that view, the object's interior might be a patchwork of partially altered layers, each representing a different chapter of its journey across the galaxy. If this is true, then studying 3I, Atlas, could offer a rare glimpse into the long-term evolution of icy bodies outside any heliosphere, something we've never been able to directly observe before. But this deeper view, whether the interior is pristine, fractured, layered, or heavily altered, leads to a larger and more difficult question. If 3I, Atlas, has been shaped more by its time in interstellar space than by its home star system, what does that tell us about where it came from and how long it has been traveling? Determining the origin of an interstellar object is one of the hardest challenges in astronomy. Gravity reshapes trajectories over millions of years, and over billions, any precise path becomes effectively erased. Still, now that Mars-based measurements have refined 3I, Atlas's outbound motion, researchers attempted what they always attempt with an interstellar visitor, to trace its path backward through space. The results were familiar, but still striking. As models ran in reverse, 3I, Atlas's path extended into the outer regions of the Milky Way, the galactic frontier where stars are older, sparser, and chemically distinct from the Sun's neighborhood. This is not surprising. Many interstellar objects are thought to originate from systems that formed early in the galaxy's history. But the estimated age range, between roughly 7 and 12 billion years, based on compositional inferences and dynamical modeling, places 3I, Atlas, potentially billions of years older than our own solar system. These age estimates are not confirmed, but they are consistent with current theoretical expectations for ancient, radiation-processed interstellar bodies. If true, that would mean 3I, Atlas, was already drifting through space long before the Sun ignited, long before Earth existed, long before the planets of our solar system took shape. And that raises an important scientific point. An object that old would have crossed through multiple stellar neighborhoods, each with its own radiation field, stellar winds, and gravitational interactions. Over that immense timescale, most objects would either fragment, become gravitationally captured, or be perturbed into different trajectories. That 3I, Atlas, still exists as a coherent, intact nucleus, suggests unusual durability, possibly due to the same radiation-hardened crust that now surrounds it. Another clue lies in its trajectory inclination. Interstellar objects typically enter the solar system at steep or randomly distributed angles, reflecting the chaotic nature of galactic motion. But 3I. Atlas entered on a relatively low inclination path, still interstellar, still hyperbolic, but smoother and more planar than expected. This doesn't imply anything extraordinary, but it does suggest that its long-term journey may have been less chaotic than that of other visitors. Perhaps it avoided dense star-forming regions or high-mass stellar clusters, traveling instead through quieter interstellar corridors. Or perhaps it was ejected from its home system with a trajectory already aligned with a flatter orbital plane, preserving some of that directionality across cosmic time. These ideas remain speculative, but fit within plausible galactic dynamics. Another question concerns the ejection mechanism. Interstellar objects can be thrown out of young planetary systems by interactions with forming gas giants. More violent events can eject debris during stellar evolution, for example, when stars expand into red giants and destabilize their planetary systems. Some early papers have even proposed that ancient binary star systems are efficient at flinging material into interstellar space. If 3I, Atlas, came from such a system, its path and composition might contain subtle hints of its origin. But so far, no specific parent star has been identified. Given its likely age and its long journey, that may never be possible. What scientists can say, based on current data, is that 3I, Atlas, appears to be a long-term drifter, shaped more by the interstellar medium than by any particular star. Its chemistry, crust thickness, and coma behavior match what models predict for an object that has endured countless radiation cycles and temperature extremes. Yet the more astronomers piece together its past, the more a new question forms not about where it was, but about where it is going. Because now that its trajectory is known with far greater precision thanks to the Mars spacecraft, researchers can examine its outbound course with much more confidence. And that course holds another piece of the puzzle, one that connects its past, its present behavior, and what it might become as it leaves our system behind. Because the next major question scientists are asking is this: now that 3I, Atlas, is heading back into interstellar space, what does its future trajectory reveal about its stability, composition, and long-term evolution? And does it behave like an ordinary comet, or something stranger? With the inbound arc now well constrained, and the Mars spacecraft providing far sharper positional data, astronomers have turned their attention to the outbound phase, a part of the journey that often exposes physical properties hidden during the approach. Now that 3I, Atlas, is cooling, shrinking, and drifting away from the sun's influence, its trajectory becomes a kind of diagnostic tool. For most comets, the outbound path is where non-gravitational forces become easier to measure. As jets turn off, as sublimation slows, the motion of the nucleus transitions toward a purely gravitational curve. But the timing of this transition, the point where activity no longer alters the orbit, can reveal important clues about the size, density, and internal cohesion of the object. With 3I, Atlas, early outbound observations hint that the transition may be happening faster than anticipated. Several teams reported that the comet's motion quickly settled into a smooth hyperbolic trajectory with fewer detectable deviations than expected for its observed activity level. This doesn't mean the comet is inactive. Spectroscopic signatures of gas are still being reported, but it suggests the gas release might not be strong enough to significantly reshape the orbit. This aligns with a picture in which the radiation-formed crust moderates outgassing, creating a more controlled, steady release rather than chaotic jets. If true, it reinforces the idea that interstellar comets may behave differently from typical solar system comets, not because they are exotic, but because billions of years of exposure to cosmic rays fundamentally change how their surfaces respond to solar heating. Another important component of the outbound trajectory is spin evolution. For comets with irregular activity, the rotation rate often changes after perihelion. Jets can accelerate or decelerate the spin, or shift the orientation of the rotation axis. But so far, no clear or confirmed rotational acceleration has been detected for 3I, Atlas. Some brightness modulations have been interpreted as possible rotational signals, but they remain unconfirmed. If the rotation is indeed stable, it would represent another indicator of a tightly sealed or uniformly active outer shell. Then there is the question of fragmentation. Several solar system comets break apart after perihelion due to internal weakening or sudden thermal stress. But fragmentation typically leaves obvious signatures: sharp brightness drops, distinct secondary nuclei, or spreading debris trails. As of the latest outbound imaging, none of these features appear associated with 3I, Atlas. The nucleus seems intact, with no confirmed secondary fragments. While this status could change with future observations, it supports the idea that the crust provides structural reinforcement. These behaviors, stable rotation, minimal outbound perturbations, lack of fragmentation, point toward a nucleus that is either unusually cohesive or unusually insulated. In both cases, the implication is the same. This object may remain structurally intact for a long time after leaving our solar system, and that has important scientific implications. If 3I, Atlas, remains stable, it will continue drifting along a well-defined hyperbolic path into the interstellar medium. Its outbound velocity suggests it will eventually pass into deeper galactic regions, perhaps into environments even more extreme than the ones it survived before reaching us. Over millions of years, it may encounter different radiation fields, encounter distant stellar winds, or pass near other planetary systems. The question astronomers are asking now is not whether 3I, Atlas, will survive it, almost certainly will, but what it will become as the radiation-processed crust continues to evolve. Will the surface darken further? Will the internal ices migrate? Will the crust harden into something more rock-like? Or will deeper layers eventually be exposed, revealing new chemistry the next time it encounters a star? These long-term possibilities are purely theoretical, but they follow logically from known radiation physics and what we observe today. But before 3I, Atlas fades into the darkness and becomes unobservable, another opportunity remains, one that connects directly to how these interstellar visitors shape the broader story of planet formation, stellar systems, and cosmic recycling. Because the next major line of inquiry is this: now that we can track 3I, Atlas, with far greater precision than before, what does its outbound journey tell us about the role interstellar objects play in seeding or influencing young planetary systems across the galaxy? In recent years, a growing body of research has proposed that interstellar visitors like 3I, Atlas, may play a far larger role in cosmic evolution than previously assumed, not just as wanderers or debris, but as seed material capable of influencing or jump-starting the process of planet formation. This idea emerged from a problem in planetary science, sometimes called the meter-size barrier. When dust grains in a protoplanetary disk collide and stick, they grow into pebbles, then boulders, then kilometer-sized bodies. But computer simulations show a gap. Objects around a meter in size tend to collide, break apart, or spiral inward toward the star rather than sticking together. So how do young planetary systems produce the much larger planetesimals required to build terrestrial planets or gas giants? One proposed answer is that the seeds don't always form in the disk itself. Instead, large pre-existing objects like 3I, Atlas, could be captured by a young star's gravitational well as it forms its disk. These captured interstellar bodies would already be hundreds of meters wide, easily bypassing the meter-size barrier, providing a stable nucleus around which dust and gas can accumulate. Recent modeling, including work from several European planetary scientists, suggests that a single forming star could capture millions of such objects over millions of years. Most would remain dormant, some would fragment, but a small percentage could become the initial cause of planets, especially gas giants. These models are still theoretical, but they match patterns observed in exoplanet surveys, where giant planets appear more common around massive stars, stars that form quickly and have less time to build planetesimals through slow accumulation. If this is correct, then objects like 3I, Atlas, are not rare anomalies. They are part of a vast galactic cycle that moves material from one star system to another, spreading chemical diversity across light years. And this brings up a fascinating aspect of 3I, Atlas itself. Its CO2. Rich composition, its radiation-altered crust, and its unusual stability are exactly the traits predicted for objects that have drifted through interstellar space for extremely long periods. These same traits may explain why such objects make ideal planet seeds. They are tough, extremely durable, and able to survive long enough to be captured inside the disks of new stars. If 3I, Atlas, formed billions of years ago around a now unknown star, then drifted through deep space before approaching our solar system, it is part of a cycle older than Earth itself, a cycle in which matter migrates between stellar systems, shaping worlds we will never see. But this raises a question astronomers are now actively studying. If interstellar objects can plant the seeds of planets, how many have passed through our solar system without being detected? And how often have they influenced the formation of planets? Here, it's a speculative question, but one grounded in legitimate scientific models. And 3I, Atlas, now that its path is more precisely mapped, may help answer it. The finer the trajectory measurements become, the more accurately astronomers can estimate how frequently objects like it cross the galaxy, and how many might pass through a forming planetary system. But to fully understand what 3I, Atlas, represents a remnant of another star's history, a migrant shaped by the interstellar medium, or something rarer, astronomers must also confront another part of its story, the anomalies that still remain unexplained. Because while many aspects of 3I, Atlas now make sense within standard comet physics, others still don't. And the next section dives into those puzzles, the kind that keeps scientists cautious, curious, and, in some cases, quietly unsettled. Even with the improved trajectory data, the stabilized outbound motion, and increasingly refined photometric measurements, several features of 3I, Atlas remain unresolved. Not mysterious in a sensational sense, but scientifically stubborn. These are the details that don't slide neatly into the existing models, even when researchers account for radiation processing, crust formation, and irregular sublimation. The first anomaly is the persistent lack of a dust tail. Comets approaching the Sun typically release fine dust grains that reflect sunlight and form the classic sweeping tail. Yet for 3I, Atlas, most observations from ground-based telescopes, space coronagraphs, and once again, Mars orbiters show a coma dominated by gas emission with either an extremely faint or non-existent dust component. There are natural explanations. Some comets are genuinely dust poor, others release dust grains too large to scatter visible light efficiently, and CO2, driven out gassing can, sometimes suppress the classic dust signature. But these explanations are still being debated because none of them fully reconcile with the strength of the earlier brightness spikes. Another anomaly lies in the color changes reported during the inbound phase. Several observatories noted shifts toward a bluer spectrum, coinciding with increases in activity. These shifts are typically associated with C2 and CN emissions, which indicate the release of carbon-bearing materials. But the timing and magnitude of those color changes were irregular, not following the smooth, temperature-dependent progression expected from standard sublimation. Spectroscopically, this suggests localized pockets of volatile material, possibly beneath the crust. This interpretation is plausible, though not yet confirmed. If the surface fractures intermittently, releasing different molecules at different times, the observed color changes would make sense. But without a consistent rotational signal to anchor these variations, the sequence remains difficult to map. A third anomaly involves brightness asymmetry. Even now, on the outbound leg, some instruments detect slight differences in brightness, depending on angle of observation. These variations could be signs of an irregularly shaped nucleus or localized activity zones, but they could also result from the crust's uneven reflectivity, another consequence of radiation processing. Because the exact shape of the nucleus hasn't been directly resolved, both interpretations remain open. The most subtle anomaly, however, involves timing. Several observed changes: the early brightness fluctuations, the asymmetric coma growth. The initial blue-shifted emissions occurred slightly earlier or later than standard thermal models predicted. This suggests the surface does not respond uniformly to solar heating. Instead, different regions may activate at different thresholds, producing behavior that appears out of sync with what thermal equilibrium models typically forecast. Again, this isn't unprecedented. Comets with layered structures or volatile-rich interiors can behave similarly, but for an interstellar object with an ancient crust tens of feet deep, the timing irregularities hint at complexity not fully captured by current models. None of these anomalies individually imply anything extraordinary, but taken together, they paint a picture of an object that resists simple categorization, one that has been shaped by both the environment it formed in and the immense stretch of space it has crossed since. This is exactly why researchers emphasize caution. They acknowledge the uncertainties, they highlight what is confirmed, and they clearly separate what is speculative, because the final anomaly, subtle, easily overlooked, but potentially revealing, doesn't come from brightness or color or chemistry. It comes from the way 3I Atlas interacts with solar radiation itself, and how that interaction might be evolving now that it is moving away from the Sunday. And that leads directly into the next major question astronomers are studying. As 3I Atlas cools and fades, does its radiation-processed crust continue to change, and could those changes reveal the true structure beneath it? As 3I Atlas moves farther from the Sun, its outward journey becomes more than a simple trajectory to track. It becomes a natural laboratory for studying something we rarely get to observe directly: how a radiation-processed surface changes after an interstellar object experiences close solar heating. If the crust is truly tens of feet thick, as simulations inspired by JWST spectra suggest, then the Sun's heat would not have penetrated deeply. Instead, only the uppermost layers would have undergone rapid expansion, contraction, and structural stress. This is confirmed by models of cosmic ray-altered ices, which show strong thermal response in the first few tens of centimeters, then diminishing influence with depth. One expected consequence is thermal cracking. As the object cools, the same outer layers that softened or flexed during perihelion begin to contract. When contraction happens unevenly, which is likely given 3I Atlas's asymmetric coma, microfractures form. These fractures can act as vents, exposing slightly fresher material beneath the surface. In typical comets, this process can lead to faint jets or small brightness bumps. In 3I Atlas, this may be a partial explanation for subtle outbound fluctuations already recorded in early post-perihelion data. These observations exist, but they are still undergoing review. Another effect involves radiation-driven chemistry. The crust isn't just physically altered, it's chemically transformed. Cosmic rays can fracture water ice, turn CO into CO2, and synthesize complex carbon compounds. When the Sun heats this surface, some of those products are released, producing the unusual spectral signatures reported earlier, including the blue-shifted emissions associated with carbon radicals. As cooling continues, the chemical pathways shift again, sometimes generating faint but detectable changes in the spectrum. These chemical transitions are supported by laboratory experiments on irradiated comet analogues, though how accurately those analogues reflect an object billions of years old remains uncertain. A more complex concept involves gas migration beneath the crust. When solar heat penetrates into deeper layers, buried ices sublimate slowly, creating pockets of gas that seep outward through the crust. As the nucleus cools, these pockets shrink or collapse, altering internal pressure. This can produce temporary asymmetries in the coma, even after primary activity fades. Some researchers believe this may explain the slight outbound brightness oscillations reported by several teams, a plausible but not yet confirmed interpretation. If such pressure-driven migration is happening inside 3I Atlas, it implies the interior remains partially active, a detail with implications for how the object will evolve over the next few months. But the most important reason scientists are watching the cooling phase is this. If cracks widen or new vents open as thermal stress relaxes, material from beneath the radiation crust may finally become visible. This could reveal whether the interior is truly primitive, whether it contains layered volatiles, whether its chemistry differs significantly from the outer shell, and whether the dust-poor coma is a surface phenomenon or a deeper characteristics. Any such change, even a small one, would immediately alter the spectral signature of the coma. Astronomers are already preparing for this possibility. Several observatories have scheduled repeated spectroscopic sessions throughout the outbound months, hoping to catch a shift in emission lines that would hint at deeper material becoming exposed. This phase is critical because we may never get another chance. Once the comet fades beyond detection limits, all remaining questions will become matters of modeling, inference, and speculation. And that leads to the next major topic in the story of 3I, Atlas, something that bridges both science and methodology. How Mars orbiter data, Earth-based observations, and space telescopes must all be combined to interpret a single interstellar object, and what limitations still remain. To fully understand an object as complex and distant as 3I, Atlas, astronomers rely on something that rarely comes together so cleanly. A multi-observatory, multi-angle dataset gathered from Earth, space telescopes, and now Mars. Each vantage point provides different information, none complete on its own, but together forming a more coherent picture. From Earth-based telescopes, researchers gain long-term photometric and spectroscopic baselines. These tell us how the comet has brightened, faded, and changed color over time. Ground observatories have provided the majority of the spectral data, showing carbon-bearing emissions and the unexpectedly subdued dust component. These measurements are confirmed, but still require further calibration as the comet dims. From space-based coronagraphs SOHO, stereo, and GOES astronomers observe the comet against the intense glare of the sun, something impossible from Earth's surface. These platforms provided the first clear detection of 3I, Atlas's elongated, dust-poor coma near perihelion. While the images are low resolution, the timing and morphology recorded by these instruments are considered reliable. From JWST, researchers obtained the high-resolution infrared spectra that hinted at the depth and chemical transformation of the radiation crust. JWST's data is robust, but the interpretation, especially the inferred crust depth, remains partially model-dependent. And finally, from Mars-orbiting spacecraft, astronomers gained something they rarely have: a completely different geometric angle on the comet's position and coma structure. This allowed for a far more precise orbital solution. The reported tenfold improvement in trajectory uncertainty comes directly from this unique vantage point, as confirmed by multiple astrometric analyses now circulating in the research community. Each dataset has limitations. Earth's atmosphere filters out portions of the ultraviolet spectrum. Space coronagraphs provide only coarse shape information. JWST cannot observe continuously due to scheduling constraints. Mars imagery, while precise, covers only a narrow temporal window. This patchwork might seem like a drawback, but in the case of 3I, Atlas, it's an advantage, because combining these observations allows astronomers to separate what is instrumental, what is geometric, and what is intrinsic to the comet itself. For example, when Earth-based telescopes detected color shifts that didn't align with brightness changes, Mars images helped confirm those shifts weren't artifacts of viewing angle. When SOHO and stereo detected an elongated coma with no dust tail, JWST spectra confirmed that the emission was gas-dominated rather than obscured by glare. When trajectory solutions from Earth diverged slightly during the inbound phase, Mars astrometry resolved the discrepancy, showing that the true motion was smoother than previously thought. This multi-layer alignment builds confidence in the core observations. 3I, Atlas is dust-poor, CO2, rich, radiation-hardened, and moving along a more stable path than expected. But there is still one challenge. Even with all this data, the nucleus itself remains unresolved. No telescope, not even JWST, has directly imaged its shape. Everything we know about its size and structure comes from indirect measurements, brightness curves, coma shape, gas production rates, and models. This means that despite tremendous progress, the physical form of 3I, Atlas, is still a mystery. And that mystery leads directly into the next section, one focused on what scientists can infer, what they cannot, and why the nucleus of 3I, Atlas, may hold the final clue to understanding this interstellar traveler. Its size, its density, and whether it behaves like a loosely bound comet or something far more resilient. Despite the extraordinary amount of data collected, no telescope has directly resolved the nucleus of 3I, Atlas. Not JWST, not ground-based observatories, not solar coronagraphs. Everything we know about its core, its size, density, and structural integrity must be inferred from indirect measurement. This is common with faint comets, but with an interstellar object, the implications carry extra weight. To estimate the nucleus's size, astronomers combined brightness measurements with the absence of a strong dust tail. The reasoning is straightforward. A dust-poor coma often reflects a relatively small active surface area, which in turn suggests a compact nucleus. Early estimates place the diameter somewhere between 200 and 400 meters. These numbers are approximate and model-dependent, but they are consistent with the faintness of the object and the observed gas production rates. But size alone tells only part of the story. The more significant clue comes from structural integrity. Most small comets are fragile, loosely bound aggregates of icy fragments and dust grains. They spin irregularly, shed material easily, and often break apart after perihelion due to thermal stress or tidal forces. Yet so far, 3I, Atlas, has shown no confirmed signs of fragmentation, despite its deep perihelion passage, despite the observed brightness spikes, and despite venting CO2, rich gas. This resilience suggests one of two things. One, the nucleus may be unusually cohesive, not necessarily rock-like, but bound strongly enough to maintain shape under stress. This could result from a radiation-processed crust, acting as a rigid shell, providing mechanical stability. Two, the dust ratio may be genuinely low, meaning the comet is composed largely of volatile ices with fewer embedded rocky grains. Such a composition might fragment differently or not at all compared to typical comets from our solar system. Both interpretations remain plausible, and neither is confirmed. But the third clue is more subtle: the rotational behavior or lack of clear evidence for it. Most comets exhibit rotation-induced variations in brightness as different surface regions face the sunday. Yet with 3I, Atlas, no consistent periodicity has been established. Some reported fluctuations could be rotational signals, but they are faint, irregular, and inconclusive. If the nucleus rotates slowly, or if the surface is uniformly darkened by radiation, rotational signatures could be suppressed. A slow or stable rotation would also help explain the surprisingly smooth outbound trajectory. Objects with slow rotation often experience more uniform gas release over time, reducing unbalanced thrust. Then there is the matter of density. If the nucleus is cohesive, its density might be higher than that of typical comets. But without a clear rotational period or fragmentation event, density estimates remain speculative. The lack of strong non-gravitational acceleration hints that the object may be moderately dense enough that solar-driven jets cannot significantly alter its path. All of this, size, stability, rotation, and density, paints a portrait of a nucleus that is more intact, more durable, and possibly more ancient than typical solar system comets. But the true puzzle is not just what the nucleus is, it's what it has survived. If 3I, Atlas, is indeed billions of years old, traveling unprotected between stars, enduring continuous radiation bombardment, and passing near unknown stellar environments, its survival raises profound questions about the durability of interstellar bodies. And this leads to a deeper topic, one that merges astrophysics with planetary science and even touches on the limits of what we consider natural comet evolution. How an object can remain intact for billions of years in the harshest environments in the galaxy, and what that endurance implies about its internal structure and history. Survival in the interstellar medium is not easy. Between the stars lies a harsh environment shaped by cosmic rays, micrometeoroid impacts, temperature extremes, and unpredictable radiation fields. Small, icy bodies face constant erosion. Over immense timescales, most are fractured, sputtered into debris, or gravitationally perturbed into destructive encounters. That 3I, Atlas, remains intact today is scientifically remarkable. One reason for its durability may be the radiation crust. Layers hardened by cosmic ray processing form a natural defense. Laboratory studies show that over millions of years of exposure, the outermost ice becomes compacted, chemically altered, and strengthened. Given billions of years, this crust can grow thick enough to shield the interior from further damage. It's a plausible explanation for why 3I, Atlas's core, remains structurally coherent, but the thickness of this crust and how deep radiation processing penetrates remains model-dependent and not directly confirmed. Another factor is its likely trajectory through quiet regions of the galaxy. If 3I, Atlas spent most of its life traveling through low-density interstellar environments, far from supernova remnants, star-forming regions, or dense molecular clouds, it would have avoided some of the most destructive radiation conditions. This idea is consistent with dynamical simulations showing that objects on long-duration, hyperbolic paths often drift along relatively stable, low-interaction corridors. Still, without a precise origin point, this remains a reasonable but unproven scenario. Then there is the question of collisions. Micrometeoroids in interstellar space can erode or puncture an icy object. Over billions of years, even small impacts add up. Yet because 3I, Atlas, is still active, producing gas and maintaining a coherent coma, it likely avoided catastrophic collisions. Its radiative shell might also help absorb smaller impacts, distributing force across the hardened surface rather than shattering the nucleus. Another key factor is thermal stability. Unlike objects within a star system, interstellar comets spend most of their time at extremely low temperatures, where sublimation is nearly non-existent. With minimal heating cycles, 3I, Atlas would have experienced little internal stress. This long-term cryogenic stability may explain why volatile rich layers survived beneath the crust. But even with these explanations, the survival of 3I, Atlas, for billions of years hints at something else. The interior might be denser and more cohesive than expected, or at least structured in a way that grants exceptional resilience. Not solid rock. Nothing suggests that, but an icy matrix capable of enduring repeated radiation cycles without collapsing. This endurance is not merely an interesting trait. It has consequences. If interstellar objects can remain intact for such long spans of time, then the galaxy may be filled with countless ancient travelers, each one carrying chemical signatures from different stellar eras, each a small archive of the environments it has passed through. And that brings astronomers to a compelling idea. 3I, Atlas might not be just a fragment from another star system. It might be a time capsule, shaped by billions of years of galactic evolution, holding within it the chemical fingerprints of epochs long erased elsewhere. This possibility elevates the scientific value of every observation. Each measurement, each spectrum, each trajectory update may reveal not only where the comet came from, but the environments it endured across cosmic time. But such ideas require caution. The durability of 3I, Atlas, can be explained through known physics, radiation shielding, low temperature preservation, coherent structure. No extraordinary mechanisms are required. What makes it fascinating is not that its survival is impossible, but that its survival is informative. And that leads directly to the next major question, one that connects deep time durability to present-day observations. If 3I, Atlas, is indeed a survivor of countless interstellar environments, how does that long history shape the anomalies we see today, and could some of its behavior be echoes of events that happened billions of years ago? Now comes a deeper question. Could some of the strange behaviors we observe today, the irregular outgassing, the color shifts, the suppressed dust, the asymmetric coma, be rooted not in its present conditions, but in processes that occurred millions or billions of years ago? This isn't speculation for drama. It's a genuine consideration in the study of ancient interstellar bodies. Radiation, micrometeoroid impacts, and long-term chemical alteration don't just affect the surface, they can sculpt the internal structure in ways that influence behavior long after the original environment is gone. One example is volatile segregation. If 3I, Atlas, endured multiple temperature cycles near distant stars earlier in its journey, certain ices might have migrated inward or outward, forming pockets or layers. As the comet warms again near our sun, these pockets could activate independently, releasing gas at irregular intervals. This could explain the mismatched timing of brightness spikes, not the result of current heating alone, but of ancient internal architecture. Another possibility is partial crust collapse. Cosmic rays break chemical bonds and restructure ice. Over billions of years, weakened layers may collapse inward, creating cavities or channels. As the sun warms the object, gas trapped in these cavities could escape through small vents, producing asymmetric jets, even if the surface appears uniform. This would create exactly the kind of subtle, localized activity seen in several spectra and reported brightness modulations. These mechanisms are plausible, though unconfirmed. A third idea involves chemical inheritance. Interstellar radiation may have synthesized complex organics within the upper layers of the nucleus. When these materials warm, they can break down, releasing unusual gas signatures. Some of the blue-shifted emissions associated with carbon radicals could reflect this ancient chemistry rather than simple sublimation. Laboratory studies support this pathway, although linking it directly to 3I, Atlas requires more data. There is also the cumulative effect of micrometeoroid scarring. Tiny impacts over billions of years could create a pitted structure beneath the crust. When heated, such a microtopography could cause localized heating differences, altering the timing of gas release. Some solar system comets show similar behavior, though on much shorter timescales. For 3I, Atlas, the scale would be magnified by its age. These mechanisms all share a common theme. The past shapes the present. The anomalies we see today may be the signatures of environments long gone, environments that shaped the object's internal landscape long before it encountered our Sunday. The idea is not that 3I, Atlas, is hiding secrets in a dramatic sense. It is that every layer of its structure, every volatile pocket, every fracture is a historical record. The irregular activity we detect now may simply be the narrative of its evolution written in the chemistry and physics of deep time. This perspective reframes the analysis. Rather than asking why 3I, Atlas behaves differently from solar system comets today, astronomers are increasingly asking what earlier environments could have produced the internal conditions we see now. And that question leads to an even broader investigation. If much of 3I, Atlas's behavior is shaped by its ancient past, what can these behaviors tell us about the environments it passed through, and can we reconstruct pieces of its galactic history from the clues it leaves behind? For months, astronomers have watched 3I, Atlas carve a clean, hyperbolic line through our solar system, a brief passage in a journey that began long before Earth even existed. The Mars orbiter data rewrote its trajectory. JWST revealed a crust shaped by cosmic rays older than our Sunday, and every telescope, from Earth to space to Mars, captured a different angle of a story that blends physics, chemistry, and deep time evolution. The mysteries that remain aren't signs of the extraordinary. They are reminders of how little we have sampled the galaxy beyond our own system. Its suppressed dust, its irregular color shifts, its asymmetric gas release, its stubborn structural resilience. Each observation hints at layers of history, written into the nucleus long before 3I, Atlas, ever crossed paths with our telescopes. And now, as it fades into the outer darkness and the sun's warmth drains away from its crust, our window into this visitor is closing. Soon its spectrum will dim past detection. Its coma will collapse into silence, and the object will become what it was for billions of years, a solitary speck drifting through the interstellar medium. But it leaves behind something valuable. It reminded us that the galaxy is not empty. It is filled with travelers, ancient fragments of broken systems, shaped by radiation and time, carrying chemical memories of environments we will never see. Atlas is one of them, a survivor, a messenger from epochs long erased. Its trajectory is now known, its chemistry partially decoded, its anomalies documented, debated, and scrutinized with the best instruments humanity has ever built. And yet, the most important thing 3i Atlas gives us is perspective. It shows that interstellar visitors are not rare accidents. They are part of a larger galactic process cycling material between stars, seeding new systems, preserving the signatures of ancient ones. Objects like Atlas may be among the oldest physical artifacts humanity will ever observe. As Atlas leaves our solar system for the last time, heading back into the deep black between stars, it carries its secrets with it. But the questions it raised about formation, evolution, and survival across cosmic time will shape how we study every interstellar object that comes after. And one day, whether years or decades from now, another visitor will appear. When it does, we'll be ready, with better instruments, better models, and a deeper appreciation for what these travelers represent. Until then, 3i Atlas continues onward, silent, ancient, unbothered, returning to the vast galactic ocean it has crossed for billions of years. A brief visitor, a long journey, a reminder of how much more there is to learn.